Good day all. Today we are starting on transformation of equation, plotting of graph with our composite table to compute a simple pendulum experiment in which we are asked to determine the value of acceleration due to gravity g and to calculate the height from the ceiling to the floor. The given equation for the simple pendulum experiment is given by 2t is equal to 2 pi square root of h minus x over g all under square root. Given this experiment, the setup are done and we have the table. From the table, we have a table of x given with our time t1 and t2 all in seconds. Now, this setup has a sketch like this. If this is the ceiling and we have a simple pendulum bob where this is our floor, we are given a meter rule. And this meter rule, we take the height from the floor to the tip of the bob. The experimental setup says we'll start by taking the height from the floor to the tip of the bob at x is equal to 20 centimeters. Then we roll over the bob to another 20 centimeter. We take our x2 to 40 centimeter and we do it subsequently till we reach x at 120 centimeters. Now, we have already found our table. Our table is given as this, whereby we have x in centimeters and we converted this x in centimeters to x in meters, dividing by 100. We have the time taken for 20 oscillation, where n is given by 20, the number of oscillation. This is t1 and t2. We take the t averaged to give us the t average here. Now, since our equation says t is equal to 2 pi all into the square root of h minus x over g, we have a task. This task is what are we going to plot from this equation that is on the table. This has been a difficult thing for students to unravel this equation. First of all, any equation that has square root can be resolved by taking out the square root, which gives us t squared is equal to 4 pi squared into h minus x over g. Aside, I would like you to know that anything under square root h over x is the same thing as h minus x over g all to the power of half. So when we multiply by 2 here, the 2 cancels out. And what we do here, all the parameters that are not under the square root will have 2 at their powers. And these 2 at their powers, we arrived at this equation. Now, we have to open the bracket, whereby we have t squared is equal to 4 pi squared h over g minus 4 pi squared x over g. Because simple algebra tells you that h over x over g is the same thing as h over g minus x over g. Now, since this equation is being transformed to a linear graph, we have to rearrange it so that we'll know where our slope and intercept will fall into. Rearranging it, we have t squared is equal to minus 4 pi squared x over g plus 4 pi squared h over g, whereby it forms a simple straight line equation like this, whereby our y-axis is t squared, this x-axis is what we got from our x on the table here, while our intercept stands for the whole of this thing here, and our slope carries minus 4 pi squared over g as the slope of the graph. So therefore now, we have to continue. From this, it has shown us here that x-axis is the x on the graph here, which we have converted to meters, and t is the t squared here. So we go on straight and plot our graph and compute our results. The title of this graph is a graph of t squared, which is second squared, versus what? X in meters. If we want to take the scale of this graph, we check our y-axis. Our y-axis is made of t squared in second square. From this graph here, t squared here has 11.06. We got t squared from the t average. We have 20 oscillations, and we have 20 oscillations. The period is the total average divided by 20, where it's like this, t average over 20. And when we got this t, we square it, because our t on this equation is t squared. So now let's go back to our graph. From our graph, our y-axis is t squared. If we want to get the scale on the t squared or y-axis, we check out the highest, the maximum number of points. Here, the maximum figure here is 11.06 and the minimum is 6. So if we count each of our graph here, for each centimeter here, from here to here, we have 24 boxes. So at 12 box, we can repeat itself again to give 24. Since 11 is the highest, we can take 2 boxes to 1 centimeter, which is taken here as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have even exceeded up to 12 centimeters here. So now, this scale shows that 2 centimeters represent 1 unit on our t squared axis. So let's go and find the scale on the x-axis. If you check on our x-axis, the minimum is 0.2 meters and the maximum is 1.2 meters. So if we can go at 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0, 1.1, and 1.2. It cannot repeat itself because we have covered almost more than half of the graph. So therefore, this slope at the x-axis in centimeters stops here. And we have 1 centimeter represents 0.1 unit on the x-axis, whereby 1 centimeters represent 0.1 unit on our x in meters axis. So therefore, since we have computed our composite table, let's go straight forward and sort the points. We have 0.2 stands for 11.06. At 0.2, we go straight to 11.06, which we have our first point here. We go to the second one, which is 0.4. It starts at 9.7 here. If you check here, 0.4, this is 0.4, starts at 9.7. So 0.4 goes to 9. This is 9.5, 9.6, 9.7. So we plot our points here. The next one is 0.6. From our table here, 0.6 corresponds to 8.85. So if this is 0.6, let's take it to 8, 8.5, 0.6, 0.7, 0.8. This is 8.85. The next one is 0.8. At 0.8, from our table, we have 7.81. So let's go to the graph and see. At 0.8 here, we have 7.81. This is 7, 7.5, 0.6, 0.7, 7.81. So let's go to the next one, which is 1.0. At 1.0, we have 6.89. So let's take the graph. At 1.0 here, let's go to 6.89. This is 6.5, 0.6, this is 6.8, this is 6.89. We have 6.89. So now, let's go to the last one, which is 1.2. At 1.2, we have 6.18. So let's go to the graph. This is 1.2. This is 6.18. So this are our points. So now let us get the line of best fits. Line of best fits is the line that cut across the points into equal halves. Now here, we can see here, if we are going to take it like this, we have our line of best fits here. So now, let me take it like this to have a good line of best fits. So let me draw a large right angle triangle to form our slope. Let me take it here, take it down here. So now, this is our slope. The task here is for us to compute the slope and find the intercept, in which we are going to extract our acceleration due to gravity and the height from the floor to the ceiling in the laboratory. So let's go on and see. From our graph here, slope m is given by t2 squared minus t1 squared over x2 minus x1. Now, let me write it on the plain sheet for you. So if our slope m is t2 squared minus t1 squared over x2 minus x1, then the value of t2 squared, which is here, this is t2 squared, is going to be 11.0 seconds squared minus, this is 4.5 seconds squared as our t1 squared. So let's go for x2. x2 is here. Please, this is a left triangle, which is a negative slope. So we should not mistaken our x2 to be at this extreme end, but our x2 is the one closer here, which gives us 0.1, while our x1 is here. If we trace it gently, we'll have here. So this is 1.3, 1.4, 1.5, this is 1.57. So now, let me bring it back. Our x2 is 0.1 minus 1.57. So now, we are going to compute our slope, m. By computation, we have a 1.57, 0.1 minus 1.57, we have 11 minus 4.5, we're going to have 6.5, sorry. So 7.5 plus 11.0 minus 4.5, this is 0, this is 10, this is 5, 10, 6.5. So we have 6.5 all over 1.47 negative. This is going to be our slope.